Good morning, everyone. Now you can hear me. Thank you for the invitation to be here. I'll talk about one of the classic models of chaotic diffusion, the Lorentz gas. And I'll give a little survey of results, that what we know to date, both in the classical setting of dynamical systems, and I also spend a small part of the lecture in the end to talk about the quantum Lorentz gas. So, good morning, Mauro.
Sorry I'm late.
Have a seat, relax. Here is the setting of the Lorentz gas. Most of you know it. So we take a point set in Rd, so a locally finite subset. We assume it has constant density. We're looking at a homogeneous setting here. So this means that the number of points in a big ball is asymptotic to the volume of the ball. Now we put on each of those points a spherical scatterer of radius r. The particles itself is called the Lorentz gas because you imagine it to be an ensemble of point particles moving through those scatterers, this array of scatterers, but they are not interacting with each other, unlike the Boltzmann gas. And we move with constant velocity between scattering events, and then we hit a scatterer, and we use the standard law of specular reflection. Of course, we can assume without loss of generality, because speed is conserved in the scattering event, that it's 1. Later on, our theory will also allow us to replace the hard sphere scatterers by potentials, but I come back to that. Now, as I mentioned, the Lorentz gas is one of the fundamental models for chaotic diffusion, and over the years there has been a number of absolutely important results in this field. In the case of fixed scattering radius, we have a central limit theorem in the case of finite horizon, which was first proved by Bunimovic and Sinai in 1980. So finite horizon means that the free path length, so the path between collisions, has a uniform upper bound. There have been many generalizations of this result by, for instance, Melbourne and Nickel, and you find many references in their paper. All of this holds only in 2 dimensions. In the infinite horizon case, Blecher pointed out that we should have a central limit theorem in the infinite horizon case, however, with a t log t mean square displacement, and that is due to channels that you have where particles can fly an unbounded distance, and these events make a non-trivial contribution to the diffusion. This was eventually proved by Zars and Value in 2007, who established this for the billiard map, and by Dolgopiat and Chernov a couple of years later, who proved the CLT for the flow, and also functional central limit theorems. So that's the situation in dimension 2. In higher dimensions, we know much less. So even in 3 dimensions, we currently don't have a central limit theorem. The difficulty here is the control of growth of singularities in the flow, and you can look at papers by Chernov and Balin and Todt, who pointed out the sort of exponential proliferation of these singularities. Another problem in higher dimensions, in the infinite horizon case, is the existence or the subtle geometry of those channels. So in 2 dimensions, the channels are basically nice cylinders, but in higher dimensions they can be quite complicated. This is the state of the art when the radius is fixed of our scatterers. But when we shrink the scatterers, which is actually what Lorentz did when he proposed the model in 1904, following the classic philosophy of Maxwell and Boltzmann to look at dilute gases, and in the case of fixed scatterers, the analog of the dilute gas is to look at low scatterer density, which means your scatterers are small relative to their separation. So we fix our points at P in general. In this case, where we are periodic, it's a lattice, so we fix our lattice. And we simply take the radius of the scatterers to 0. And as I will explain to you, in this small scatterer limit, one can say much more, not only for the periodic gas, not only in 2 dimensions, but actually in arbitrary dimension. And a particular application of the work that I did with Andreas Strömbergsson is super diffusive central limit theorem, with a T log T mean square displacement, just as Blecher suggested, but this holds actually an arbitrary dimension for the periodic Lorentz gas. And that's a joint work with Ball and Todt, which was published last year. Now, when we go away from the periodic setting and the Lorentz gas, again, almost nothing is known. We do not know whether for a fixed aperiodic scatterer configuration there is a central limit theorem. The effects are very, very subtle, so even when you take a periodic Lorentz gas and you perturb a finite number of scatterers, you see very interesting effects. The best set of papers on recurrence properties, for example, for aperiodic Lorentz gas is the work of Marco Lenci and his collaborators. And I refer you to those papers. But as I said, proving a central limit theorem for an aperiodic Lorentz gas, even in dimension 2, is an open problem. So again, the question is, well, let's follow Lorentz's original idea and let's shrink the scatterers and see what happens there. So let's talk about this Boltzmann-Grad limit of small scattering radii. So first of all, of course, our phase space is position and velocity, and remember we have agreed that we take our initial velocity to have absolute value 1, so that's a preserved quantity, so that will remain 1. As you shrink the scatterers, an important quantity that I mentioned already is the free path lengths, and the free path lengths will grow. The mean free path lengths will grow as r tends to 0, and a simple measure argument shows you that the mean free path lengths grows like 1 over the volume of the total scattering cross-section of each scatterer, and that is r to the d minus 1, right? It's just the hyperdisk of the ball of radius r. So the mean free path length therefore scales like r to the minus d minus 1, or r to the 1 minus d is probably easier to say. And what that means is if you now go into this limit, you have to rescale your space and time coordinates in such a way that you capture that effect. So if you just sit there and do nothing, in the limit you'll just see a free motion. Okay, so you need to wait for longer. And also you need to zoom out in such a way that your mean free path, that all your position units are measured in units of the mean free path length. Okay, and this is done by introducing these macroscopic coordinates, capital Q and V, which is simply the microscopic coordinates with time rescaled in this way. So this makes sure you wait long enough until the first collision occurs. And you also rescale your space units by this factor. And now you consider in these rescaled units your billiard flow. And you're asking the following question. So take an initial density in those macroscopic units, F, in L1. So L1 in our phase space, which is RD cross the unit sphere. And you evolve it in the usual way. So now you have the density at time t. The important thing, of course, here is to remember that we're not looking at a fixed dynamical system, but we're now looking at a sequence of dynamical systems, which is parametrized by R. And so the question is, as we go through this limit, does FTR converge to something in a weak sense? And that's precisely what Boltzmann suggested. And he said the limit should exist. Boltzmann, of course, didn't specify exactly which scattering configuration to look at. He simply developed the heuristics where he followed, Boltzmann's classical Stoßzahlansatz, which makes certain assumptions, which of course weren't justified, but he came up with an equation that's analog to Boltzmann's equation, which is called the linear Boltzmann equation, or also kinetic Lorentz equation, which should describe the macroscopic limit of the dynamics in the Lorentz gas. And you see it here. The left-hand side is just the Liouville equation for free motion, and the right-hand side describes collision events. And in fact, what the Lorentz process is, of which of this is the sort of Kolmogorov forward equation, the Lorentz process is a Markovian random flight process, where you fly along a straight line for a time that's exponentially distributed. So when your exponential clock rings, you change direction, and you change direction according to this conditional probability density here. So given you have speed v prime, what's the probability that you have speed v? And that's precisely the differential cross-section of an individual scatterer. So the main philosophy here is of Boltzmann and Lorentz and Maxwell and so on, is that two things decouple. Your free motion decouples from the scattering events, because it's a priori, it's absolutely not clear that you should see here a single scattering event occurring, because you could have multiple scattering in theory, and that's indeed what you have when you look at fixed radius. So the idea of going to the dilute gas is that your dynamic simplifies, that you get a process which decouples the free motion and the scattering, and that's what's precisely being predicted here. Now I've written down examples for the differential cross-section in the case of our specular reflection, so this would be the formula. But this all works also when you don't have hard sphere scatterers, but scattering events given by potentials. And in this case, you would have a different scattering cross-section. This equation has found enormous amounts of applications. It describes, for instance, neutron transport in nuclear reactors. It describes radiative transfer, many other things. For instance, also I've seen a paper where people use to model water waves in the ocean in the presence of ice planks, which are the scatterers modeled by the linear Boltzmann equation. Now, it took over 65 years until there were some rigorous results on establishing the convergence of the underlying Hamiltonian dynamics, so the convergence from the billiard dynamics to the linear Boltzmann equation, and that was first done by Galavotti, who proved it in the case when your scatterers are located at points of a Poisson point process, and he proved this on expectation over the point configuration. Spohn extended this by looking at more general random scatterer configuration and looking at quite general potentials for the scattering events. And a very important paper is by Boldaghini, Bunimovic, and Sine, who proved that for a fixed scatterer configuration, which is the realization of a Poisson point process, you get convergence. So not just on expectation over all scatterer configurations, but for a fixed one. And a standard argument shows that given that the free path length in all these models is exponentially distributed, is that you get a central limit theorem for the limit process, which is a standard central limit theorem. So no super diffusion. In the quantum setting, what you do instead is you now look at a solution of the Schrödinger equation, and I'll explain a little bit about this now. So you think of the solution of a wave equation at the presence of scatterers that again can be randomly distributed in your RD. And Eng and Erdős proved precisely that in the Boltzmann-Grad limit, for smooth potentials, you again get convergence to a linear Boltzmann equation. The differential cross-section is now a quantum differential cross-section. I'll explain a little bit more about that. So that's a very beautiful result. It builds on earlier work of Erdős and Yao, where and by Spohn, where rather than looking at a low-density limit, people looked at a weak coupling limit. So you don't make your potentials very, very small and localized, but you keep them, you just decrease their strength, and you look at the limit of low potential strength. Again, I'll say a bit more about this later on. Now, that's basically the setting, and I want to now explain to you two more recent results. One in the classical setting, where we want to investigate more general scatterer configurations than just periodic or Poisson random scatterer configuration. And in the second part, I'm going to look at the periodic Lorentz gas, but the dynamics when you look at wave evolution. Okay. So, first part. So, what's really the problem here that we need to investigate in the small scatterer limit? Well, the core of the problem is to understand that if we've just hit a scatterer with from a random direction, random particles hitting that scatterer, when will they hit the next scatterer and where will they hit it? That's the basic setting, and you see here the sort of diagram of the kind of quantities one needs to look at. So first of all, we're assuming here we've just hit a scatterer that's located at a position yn, so that's the end scattering event. And after the end scattering event, we have a velocity vn. And I've already turned my picture in such a way that that velocity is sort of horizontal, but of course it doesn't have to be necessarily. So that's just the frame that I'm looking at here. That velocity Vn will be random. Why will it be random? Well, because what we do is we think of our initial particle velocity as being random. Remember, I'm thinking of a cloud of an initial particle density, which means, in other words, that we have an initial random position and initial random velocity. So this means, of course, that at the end scattering event, I'll have Vn to be random, but it's not very random because it depends on all the previous events. So it's only a function of the initial Q and V who are random. However, part of the argument is to show that we get a loss of memory, so that even though Vn is really a deterministic function of the first position and velocity, it's actually becoming more and more random. And the randomness is introduced by the convexity of the scatterers. So for you, it's sufficient at the moment to think of Vn as a random variable that is distributed according to some probability measure lambda, and assume it's an absolutely continuous probability measure, okay? Even though it's not true, but it's approximately true. So we think of this as being random, and now we also have an exit parameter here which describes the exit position of our particle relative to the plane that's perpendicular to the velocity Vn. And we want to understand, given that we exit here, what's the probability that we hit the next scatterer after a certain time tn plus 1, measured in units of the mean free path length, and that we hit it at a certain point, that we hit the new scatterer at a certain impact parameter, which is again measured in terms of the coordinate which is perpendicular to Vn. Why do we only look at this coordinate? Well, because the horizontal coordinate is not so important, right? This is of order r. So if I hit here, or if I hit sort of here or here, it's a very small time compared to the very large time that we're comparing this with. So this is an error you can neglect. You have to, of course, justify all of this. But anyway, so this is basically the geometric setting that we need to understand. And the only thing I want you to take away from this slide is look at sort of the various dimensions here. This is of order r, this kind of length units, and this length unit is of order r to the 1 minus d. Just one word on the exclusion zone. What I mean by this here is, in order for this particle to hit this scatterer here, we have to make sure that there's no scatterer intersecting this flight path here, right? And that's equivalent of saying that no center of the scatterer should be in this blue domain. Does everyone see that? Yeah, so this is just another formulation of saying, in order for this event to happen, flying from here to there, I better not have any other point of my point set P in this blue set. And this blue set is long and narrow, right? Because r is small. Okay, now we exploit this fact that we have something long and narrow here by rescaling. And that is, of course, very similar to the philosophy that you have when you're trying to do renormalization in Teichmüller dynamics and so on. So it's exactly the same philosophy. We have something long and narrow, and we want to rescale it through some group action, in this case SLDR, which makes the long directions reasonably sized and which makes the short directions reasonably sized. So I'm just applying this matrix. Now, before I do this, I have to rotate everything so I actually do get into this frame. So this is done by a rotation matrix RV. So this matrix RV is simply the one that takes my velocity at the end scattering event Vn, and it's a function that for every Vn rotates it so it becomes the horizontal vector. So when I start with my original setting with a random velocity, I therefore need to apply a matrix which is a random rotation and then this dilation matrix here. Now, in order, of course, what I need to do is apply it to the whole picture, and this induces now a dynamics on my point set P. So remember, I'm starting with a fixed point set P. I need to shift the point set so that the scatterer I'm looking at the moment is at the origin, because then I want to apply my linear rotation, my linear transformations, the rotation and our dilation. So, starting off with a fixed point set P, what I've done here is I've shifted it by the scatterer I'm looking at, and then I'm rotating it. I'm rotating it randomly because remember, Vn is a random velocity, it's a random vector. And then I'm applying the sequence of diagonal matrices dr. I'm also saying here that Yn is random. Well, why is Yn random? Because in some sense, I'm hitting a certain scatterer, and that scatterer sits somewhere randomly in my whole array of scatterers. I don't want to go into details, but that's one way of thinking about it.
Sorry, excuse me, I'm not sure I understand the meaning of psi Rn. Is it just sort of the sequence of scatterers that you hit as the particle moves, or?
So P is a point set. Is a fixed point set. Yeah. Now I'm shifting that point set. So this means it contains the origin. Yeah?
So sort of at the origin is the scatterer you just hit.
Exactly. So Yn is an element of P. Right? Yn is the position of the scatter I've just hit. So I'm shifting that to the origin.
It's environment which see from the particle.
Exactly.
So it's what you see if you sit on the particle.
Exactly. Exactly. I'm sitting at the end scatterer, okay, and I'm and then I'm rotating it so that it's in the frame where I'm looking exactly in the velocity 1. So you could say that's also from the viewpoint of the particle, because the particle just decides it's only going to look along the line it's traveling, and that's the direction 1, 0, 0, 0. But then, of course, the particle doesn't like to do that to itself because it's sort of squashing it.
So it's not clear exactly the meaning of this last transformation.
Yeah, the meaning is clear in mathematical terms. Okay? And all I want you to, so I don't want you to think too hard about this, Sasha, because what I want you to remember is just that what do we have now? We have a random point set. Psi Rn is really a random point set. What is a random point set? Really, it's a random point process. Okay? So this means it's a random measure in Rn, which is a counting measure, so an integer valued measure. That's it, yeah? Forget everything else. So we now have a sequence parametrized by R of random point processes. And really, what we would like to understand in order to solve our problem is, does this sequence of random point processes have a limit? And if it does have a limit, then we can answer all the question. What's the probability that there's no point in that exclusion region, for instance? What's the probability that I hit the next scatterer near the point that I want? Yeah? Does that make sense?
You mean statistical limit, weak limit?
Yeah, always weak limit. Because, for instance, when you ask what's the probability that there's no point in that scatter, that's like convergence in one-dimensional distributions of this point process. So if I understand it in general in convergence distribution, I know even more than I need to know, but this is the natural setting of it. So now, in order to answer this question, we need to make some assumptions on the point set P. So the first assumption is very natural. That's what I started off with. We assume it has constant density, and what this means is exactly what I've written down here. The second assumption is that when I look at this kind of sequence of random point processes, and I'm now fixing y here, in general, the limit could depend on y. It could be a different limit for every point y that I'm looking at. And that, of course, would be very bad in a sense. I mean, then we really can't say anything. We need to control the y dependence, the dependence on the scatterer that I've picked. And a crucial assumption here is that the y dependence in the limit will be nice. Okay, and what does nice mean? Well, it should be the limiting process should have a nice parametrization in terms of y. So we assign, so the way one can do this in the theory of point processes, you assign a label to each of the y's, which we call a mark. We want the space for the limiting process of those y's to be, of these marks to be nice. And this is done in the following setting. So we assume that the space of marks is a nice space, so a compact metric space with a Borel probability measure on it, and that we have a map that assigns to each of our scatterers a mark in that compact space. Okay, of course we can always do it if we don't insist on being compact, because we can just assign a label to each scatterer, which is just, you know, the counting label. So you just enumerate all your scatterers, but that wouldn't be a very nice compact space. Okay, so this is an important assumption here, that our space of marks is a compact metric space, and we furthermore assume that, so we make these definitions, we now say, okay, we have now the space RD times our mark space with a natural measure. This will now generate a marked point set. So each point now has a mark. We define the action of SLDR on this in the natural way, but just applying it to the RD component. Now, the first assumption, that's an important assumption, is that somehow the marks are uniformly distributed on our scatterers. Okay, so if we look at a large ball of scatterers, we want that the proportion of marks that fall into a certain region in our mark space is the same, has the same distribution according to our measure M. So that's assumption number one. Assumption number two is also a very important assumption, and that's the statement that indeed, now that our random point process, including the mark, so this is now a marked random point process, converges to a limit. Very strong assumption. And that's something one needs to check for each of the classes of point configurations you're looking at.
Could you comment a little bit on this assumption, say, for quasi-point process?
Yeah, I will do that. Yeah. So here, yeah. On the measure mu, nothing. Just the Borel measure, and of course this is an assumption that we have this. Yeah, and that we have this. So these are all sort of implicit assumptions on mu. So the point is, find a measure M for which assumption 1 and 2 hold. So it's not that you somehow, so it needs, the measure M is adapted to the system. And now I'm giving you some examples and you see what's happening. So first example is the Poisson process. So if you take the Poisson process, say with intensity 1, we do not need to label the scatterers. It's fine. It's homogeneous enough. Okay? So the mark space is just trivial. It's just every scatterer gets the same color. And the proof that those assumptions hold is a non-trivial proof. Okay? And we're using essentially the ideas of the paper by Bolderghini, Bunimovic, and Sine there. You had a question? No? Okay. Second example is the case of the periodic Lorentz gas, which we have understood already in earlier work. And again, there you don't need marks. And that's not surprising because, of course, we have this translation invariant. So every scatterer is the same anyway. And we do get spherical equidistribution on the space of lattices, which just follows from the mixing property of the diagonal flow on this space. Okay? Right. So, let's look at the periodic Lorentz gas where we remove scatterers at random, say by a Bernoulli process, right? So you throw your dice 50-50. If it's heads, no, it's not a dice, it's a coin. If it's heads, you remove your scatterer. If it's tail, you keep it. And in fact, in our paper, we do more general processes. They don't have to be necessarily independent. But in this case, you can check the assumptions. But here, you need to start with your lattice ZD, and your marking will be 0 or 1. Okay? So here, in a sense, you're really still working in ZD, but your point set is somehow ZD, but some scatterers are invisible. So that's also a natural example. But our main example really is when our scatterer configuration P is a Euclidean cut and project set, and in this case, a cut and project set is basically a set like the vertex set of the Penrose tiling, which can be constructed by taking a high-dimensional lattice, taking a slab and projecting all the points that are in this slab to your space RD that you're interested in. You get an aperiodic set in this way. And now the marking that we need here to prove everything is the height of the lattice point in the general construction. Okay, you don't need to, I'm just saying it. So here actually our marking is a real variable. So our compact mark space sits in this window set. And there we can establish those assumptions 1 and 2 using spherical equidistribution again in a homogeneous space using Ratner's theorem. And sort of you can read about this in a paper 3 years ago with Strömberg's on. The paper doesn't fully prove those assumptions. That's done in the new paper, because in that old paper we only looked at we proved this convergence but not uniformly in P, which is a technical assumption here. But you can find this convergence for every fixed y in that paper. And as I said, it really requires a very non-trivial application of Ratner's theorem. Okay, and then once you have this, once you have satisfied your assumptions 1 and 2, you can prove the analog of the statements that we had in the Poisson case. So a weak limit exists for a random point process. It's not, unfortunately, or maybe fortunately because it makes it more interesting, it's not Markovian. You need to extend your state space to make it Markovian, which means in particular that the linear Boltzmann equation doesn't apply, but a generalized equation applies on this extended state space. One indicator of this is that this limit here doesn't form a semigroup. It forms a semigroup only on the extended state space. Okay, so that's basically it. So here is the generalized linear Boltzmann equation, and I'm giving you here the variables that we have. So it's absolutely critical, as you see, that we have the mark space here, because the probability of starting from a certain scatterer and hitting the next scatterer will depend on the color of that scatterer and the color of the scatterer you're hitting. Okay, and that's absolutely fundamental in this setting. Plus, it also depends on your impact and exit parameters, which is encoded by having to know the velocity after the next hit. And it also depends on the flight time. So you have here an equation that looks like the linear Boltzmann equation but depends on more variables. So I'm not going to say more on that unless you have any questions. Yeah? You all ready to go quantum? All right. So now we're forgetting about aperiodic point configurations. I have no clue how to do this. Now this, of course, is a very, very fundamental problem in solid state physics, because you model crystals in this way. And already since the beginning of quantum mechanics, the 30s, people have answered a lot of questions in this. But I haven't found any really detailed treatise of the small scatterer limit. There's an area in PDE which is called homogenization theory, which looks at these kind of problems as well. You have obstacles in the plane, you look at the solution of the wave equation, and people do look at small scatterers there, but usually not in the limit when the wavelength that you're looking at, your characteristic wavelength, is comparable to the size of the scatterer. And that's exactly what we want to do here, because we would like to see a quantum effect in the scattering. And you see a quantum effect when your wavelength is comparable to your scatterer. If the wavelength would be much smaller than the scatterer, you would see a sort of semi-classical, it's a geometric optics limit. Yeah. If the wavelength would be much, much larger than the scatterer, you only see a very minor effect. That's, so that's why we're looking here at that particular limit. Now, here's the setting. So the Schrödinger equation is this PDE here. There's time, t. There's position x. We have a linear operator called the Hamiltonian, or quantum Hamiltonian, which looks like this. H here is a scaling variable. Lambda is the so-called coupling constant that I mentioned earlier in the talk. So when you look at the weak coupling limit, you take lambda to be small. V is a potential. Now typically in classic textbooks in solid-state physics, V is fixed. But here V is not fixed. We make V, we shrink V. And just exactly as in the Boltzmann-Grad limit of the Lorentz gas, a big difference here is we can only handle smooth potentials now. So we can't actually look at the classic Lorentz gas. Don't worry, Kostya, one could do it, but it's much harder. And so we take a smooth potential. So you could think of it as C infinity with compact support. This means Schwarzglas here. So infinitely differentiable, and every derivative decays faster than any power. You can write the solution of your Schrödinger equation formally as a starting with your initial density F0 and then applying this unitary operator here. V is a real valued function, so this makes this operator self-adjoint. And now we need to try to understand how we can find an analogous description of this weak convergence. Right? We can't just look at the wave function and take a limit because it's very highly oscillatory and it'll just converge to nothing. There won't be a limit. So we need to look at the weak limit. And we need to find the analog of the density that we had before evolving in time. And this is done by replacing densities by linear operators, so-called quantum observables. And I'm just telling you here that the way quantum observables evolve is just by conjugation by that unitary semigroup that I wrote down on the previous page. We introduce the usual L2 product on the classical phase space. So this is just RD times RD. Y is now not necessarily on the unit sphere, because here we need to look at a range of speeds, because a quantum particle doesn't just know that it has to have speed 1. It can't just have speed 1, generally. And we have also an inner product, Hilbert-Schmidt inner product for our linear operators. Now here is the key point. The key point is now that we want to associate with a classical observable a linear operator. And this is done by Weil quantization. This function E here is, and I still haven't put this in. I think you asked me in the last talk, Kostya, didn't you? Maybe someone else. E of x, and there's no chalk. E of x is just e to the 2 pi I x, yeah? Is that okay? No, is it okay? E of x is e to the 2 pi I x? Wasn't you? Yeah, okay.
Number theorist.
Yeah, it's a number theorist notation. And now we have to think of the scaling limit. So what we do is, starting from our classical observation, we scale our classical observable exactly in the same way as before. This normalization is just an L2 normalization. So that's the Boltzmann-Grad scaling. And scaling the momentum variable is very standard in semi-classics or microlocal analysis done in this way, and this assures that the wavelength we'll be looking at will be of order h. Okay, because the second component here, the momentum component, if you think about that, through this Weil quantization, will become the frequency of the waves that you're looking at. Yeah, that's all you need to remember at the moment. So the y's are basically characterizing the frequencies. If I choose an observable A, say with compact support in both variables, what I'm ensuring here is that basically most frequencies that I'm looking at in my wave will be of order 1 over h. So the wavelength will be of order h. And now I'm using this here to define a quantization by first doing my Boltzmann-Grad, my semi-classical Boltzmann-Grad scaling on my function h on Rd cross Rd, and then Weil quantizing it in this way. So that gives me now a Boltzmann-Grad scaled quantum observable. And now the question is, well, if we now do exactly what we've done before, so now this is like the analog of a weak limit here. We start with an observable, initial observable, scaled in this way. We propagate it according to this rule, so-called Heisenberg evolution. We test it against another fixed observable, which again is scaled in the semi-classical Boltzmann-Grad fashion. And we ask, is there a limit?
So here you don't rescale the h at all. H
No,
is fixed.
no, h is not fixed. Didn't I say this here somewhere? So h, remember, describes the wavelength here. And I'm sorry that I did not write this here. You're absolutely right. So r is equal to h in what we do here, or is of the same order. Yeah, that's crucial because, as I said, we want the radius of our scatterer to be commensurable with the wavelength. Now that's the limit we're looking at. And so this conjecture here, I wish it was a theorem, it would be a fantastic theorem, says that the limit exists. So that's the analog of what Lorentz would have predicted. Would he have known about quantum mechanics and microlocal analysis and so on? Okay, I believe. Maybe he wouldn't. But the second point is important. It's not a solution to the linear Boltzmann equation, just like in the classical setting. Now, if you look at random scatterer configurations, there is a theorem by Eng and Erdős that I mentioned earlier, which proves the first fact. Indeed, this converges, and LTA solves the linear Boltzmann equation with this particular collision kernel, which is exactly the quantum mechanical cross-section. Yeah? So, if your P's are, say, distributed according to a Poisson point process, they use a slightly different setting, but morally it's the same. Then you can prove the first statement, and you get convergence to a linear Boltzmann equation. So, what can we do in the periodic setting? We can't prove this statement, but we can do something. We can prove the statement up to second order in perturbation theory. The first thing. So let me explain what we're doing here. So LT was the limiting family of operators that describe our dynamics, and this could generate a solution of the linear Boltzmann equation, or it might not. Now, we expand this in a formal power series in lambda. Lambda was the coupling constant in front of our potential. Now, even though I think of lambda being fixed, I don't want to go into the weak coupling limit, I can still do a formal power series expansion. And let's assume the first term of this power series expansion are of this form. So the first one is just free motion. Yeah? The second one is 0. And the third one is free motion coupled with one scattering event. So you basically, and here's a typo, that should be an S here. So you flow for some time S, or maybe it's not a typo, sorry. You flow for some time S, then you scatter, it's not a typo, that should be t. So you flow for some time s, then you scatter to a new velocity v prime according to your cross-section here, and then you flow again. And you integrate over time, which is saying s is uniformly distributed in the interval 0t that you're looking at here, okay? Don't look at the expression anymore, just remember that actually if you start with a solution of the linear Boltzmann equation and you make this formal power series expansion, you get exactly those two terms, those three terms. And the theorem we have is that the object that we're interested in actually up to second order has those terms in its expansion. Okay, so we are now in the periodic Lorentz gas. This is joint work with my student Giorgi Griffin, who's now in Canada, Queen's University. If you expand the thing that we're interested in up to second order in lambda formally, then you get terms that are consistent with a linear Boltzmann equation. We can't say anything about higher order terms. We have, this is not just formal, a formal expansion in lambda, but it actually has a proper error term here. But you observe that it explodes as r tends to 0. So this would be, the way to understand this is first take lambda very, very small, and then r to 0. Yeah? So this is an indication that we indeed can expect some nice limit. That's what our conjecture is based on. Now, the way we prove this conjecture indicates that the order 4 term in this expansion, this formal expansion, actually is not that of the linear Boltzmann equation, and that's why we conjecture that the limit should not be that of a linear Boltzmann equation. I think I'm stopping now. I'll just flash the 4 points in the proof of this theorem. The first is absolutely classic in the analysis of periodic potentials, is Floquet-Bloch expansion. Alpha is a Bloch vector. We then prove on each Bloch subspace that the theorem holds under certain Diophantine conditions on this Bloch vector alpha. Then we use another textbook tool, which is the Duhamel expansion. That's a tool in perturbation theory to get these various terms. So we need to iterate that expansion. And then finally, we use a generalization of an old theorem of mine where I considered the randomness in the sequence of these quadratic forms, and an extension of that will give the second order term that I've just flashed to you. Now, if rather than just for 2-point correlations, we could have the same result, the same convergence proof for higher order correlations, then we can prove everything, but we don't have it. But if it were true, we would indeed get fourth order terms and so on that would violate the linear Boltzmann equation. So under this Poisson model, the linear Boltzmann equation would fail. And I'll stop here. Thank you.
Are there any questions, comments?
So basically, you started in early 2000s with these periodic configurations in a classical setting. And what they're doing now is just quantum variant.
2007 we started, yeah.
So you're planning to do it in a random setting as well?
Yeah, so the quantum, yeah, that would be my dream project.
It might be even easier in a sense, because periodic.
So the random setting is easier, as the results of Erdős show, but the quasi-periodic setting is very hard. So even for fixed configurations, there are very few results, rigorous results, that can understand the long-term wave dynamics.
But Poisson configuration should be kind of doable.
Yeah, that's done. So whenever you have sufficient randomness, then you can average things out, you get cancellations of your oscillatory integrals.
Okay.
Thank you. Other questions? Okay, thank you, speaker again. The second speaker today in the morning is Andrey Dymov, and he will speak on the functional limit theorem for the sine process.
Thank you very much for the invitation to this conference. And today we'll speak about our joint work with Sasha Bufetov, where we try to understand behavior of determinantial processes with a logarithmic growth of the variance in the space of trajectories, and especially of the sine process, which is one of the most important determinantial processes. I will start with some introduction, where I will recall the basic notions. In fact, Yanshi has already recalled yesterday the most of these definitions, but nevertheless I will repeat them shortly. So first, let me recall what is a random point process, and I will consider only the random point processes on R, with difference with the talk of Yanshi. To this end, let me consider the space of locally finite configurations on R, which is just which consists of all subsets of R that does not have limit points. In R. So in other words, each configuration X is just a set of points, a discrete set of at most countable number of points on the real line. And since each configuration doesn't have limit points in any bounded set, say B, the number of points can be only finite. By such sign during all the talk, I will denote the number of points in the set B. To be more formal, this number of points, of course, depends on the configuration. For example, here, this number of points equals to 3. And next, let me consider the triple, the space of configurations. Some sigma algebra which is generated, some Borel sigma algebra which is generated by appropriately introduced cylinder sets, and the probability measure on this space with this sigma algebra, and such triple is called random point process. So now the configurations are random, and this object is a random variable. Next, let me recall what are the correlation functions. So let me consider a sequence of functions rho n with n more than or equal to 1. Each function rho n is a function of n real variables, which is non-negative. The functions are assumed to be locally integrable. And they are called the correlation functions. The correlation functions if for any n sets B1, Bn, which are Borel and bounded, and which are also disjoint. So for I different from J, their intersection is an empty set. We have the following formula. If we take the expectation of the number of particles in the set B1 times and so on times the expectation of the number of particles in the set Bn, then this equals to the integral over the direct product of these sets of the correlation function rho n. So this is definition of the correlation functions. In particular, if our process would be such that almost surely we have initialization, almost surely we have only n points, then all the information would be encoded in the nth correlation function, and it would be just the probability density. However, since the number of particles can be infinite, so we really need this sequence of functions, and all the information is encoded here. In particular, each function rho n should not be a probability density in the sense that the integral of all the space can be infinite, because the number of particles is infinite. The correlation functions is a rather convenient language to speak about the point processes. In particular, in applications they usually exist, and under appropriate assumptions they define the point process uniquely. Let me give some simple example. If P is a Poisson point process with the parameter lambda, then the correlation functions are very simple. They are constant and equal lambda to the power n. Next, let me define what are determinantial processes. The point process is called determinantial. If the correlation functions exist and have very special form, namely if there exists a function k which is function of two variables, which is usually called kernel, such that for any n the correlation function with the number n has the form of determinant of a matrix with components a, I, j. This is a matrix of the size n times n, and these entires a, I, j, this is just the kernel k taken at the points xi and xj. So the correlation functions have such a special determinant form. One of the most important examples, the most known of determinantial processes, is the so-called sine process, which is given by the sine kernel k sine of xy, which is just sine of x minus y over pi times x minus y. So from the first point of view, determinantial process and the sine process, this is something very special. However, they arise naturally in different areas, like in the number theory, in the mathematical physics, and they play a very special role in the random matrix theory. Namely, if you consider the Gaussian unitary ensemble, which consists of matrices, of square matrices, which are Hermitian, which consist of with independent entiers modulo that are Hermitian, and the entiers are Gaussian, then you look at the spectrum of these matrices. Since the matrices are Hermitian, the spectrum is real, and you have, for the matrix of the size n times n, you have exactly n eigenvalues. Then they are random, and then you look at their distribution. When the size of the matrix tends to infinity, under appropriate scaling, this spectrum is governed exactly by the sine process. And there is a universality hypothesis in the random matrix theory which says that this is a regular situation for large class of Hermitian matrices, of random Hermitian matrices. So the sine process, as well as determinantial processes, other determinantial processes, is a rather natural object. Yes. Also, you have, for example, the Airy process and the Bessel process, which can be obtained in a similar way, under some different scaling, for example, for the Airy process. So here I conclude my introduction. Let me pass to the next part of the talk, which I call central limit theorem and the functional central limit theorem. In this talk, I will mainly interested in the following random variable. I take the sine process and I consider the number of particles on the interval 0, n. And I ask what happens when n goes to infinity. What is the behavior of this number of particles? And my main results will be hold for the sine process. However, if something hold for different determinational process, I will try not forget to mention it. About the behavior of this random variable, the central limit theorem is known, and it's proven by Kostin and Lebovitz in 95. This is just usual central limit theorem. So you consider the number of particles in the interval 0, n. You subtract the expectation and you normalize over the square root of the variance. And then the distribution of this random variable psi n weakly converge to the normal law. Weakly converge to the normal law. In this case, the sine process is stationary in the sense that it depends. The kernel depends only the difference of x minus y. So if you look at some window in the real line, if you move this window, the distribution inside this window doesn't change. That's why the expectation grows linearly. More precisely, it behaves as n over pi. However, the variance in this case is very different from the classical central limit theorem where it grows linearly, because it grows very slowly. More precisely, it behaves as some constant pi to the power minus 2 logarithm of n. This is because the particles under the sine process, they are strongly dependent. Despite this, the central limit theorem holds in full generality. Since that time, the central limit theorem was established, was generalized for large class of determinantial processes, mostly by efforts of Soshnikov. However, about behavior of trajectories of the sine process, basically nothing is known. And the question we ask, if the Donskian invariance principle holds for our random variable, so we want to understand if the trajectories could be approximated by the Brownian motion. In which sense can we speak about the Donskian invariance principle here? Donskian invariance principle or functional central limit theorem, what is the same? Just in a standard way, so I take my random variable which I have in the central limit theorem and I insert times a and obtain the random process psi and t, which equals to the number of particles on the interval 0 tn minus the expectation, and then I normalize over the variance, but I will write directly the asymptotic of the variance. So I write p to the power minus 1 square root of the logarithm of n. We obtain a random process. Let us say that t is between 0 and 1. Then we cover all the interval 0, n. And the question in particular is if it is true that distribution of this random process in some space of trajectories converges weakly when n goes to infinity to the distribution of the Brownian motion. And it turns out that this is not the case. This is not the case in difference with many dynamical systems for which the central limit theorem holds. And the reason is that this slow growth of the variance. If the variance would grow linearly, then we would have the central limit, the Donskian invariance principle in the usual sense. Then the question, what happens? Can we describe in some sense the limiting behavior of this process? It turns out that yes, and this is the main result of our work. So now I will formulate the result. It turns out that behavior of this process is very irregular, and the limit cannot be specified in the classical sense. It means that it doesn't live in any separable metric space. That's why, in order to regularize the dynamics, instead of studying the process itself, we study its antiderivative. So we integrate in time the process. Here you can think about, say, about the white noise, because the white noise can be defined only in the generalized sense, but the integral of the white noise gives a Brownian motion. It's a nice random process which is continuous. And then I represent this integral in the following way. I fix any time tau, which is positive and which is between 0 and 1. And I consider the random variable eta n, which is just the averaging of my process over this time interval. So I integrate psi Sn over interval 0 tau, and I divide over tau. And then I write that my integral equals to eta n t plus z tn, and over the same normalization that I have here. P to the power minus 1 logarithm of n square root. And this formula is just a definition of the process Zn. So I find the process Zn such that this holds. So this is a definition of the process Ztn. And the main result is the following theorem. The joint distribution of the random variable eta n with the process Ztn converges, when n goes to infinity, to the joint distribution of some random variable eta and the process Zt, where eta and Zt are independent. Eta is distributed accordingly to the normal law with parameters 0 and half, and the t is a centered Gaussian process whose covariances we find just explicitly, but this is a rather long formula, so I will not write it, but in 2 minutes I will explain it. Explicit formula. So before explaining what is the process Zt, let me explain what this theorem means on the picture. So we have our process, our integral of the process psi Sn. Here we have time. Then this process can be decomposed to 2 components. The first one is just linear in time process, eta n t. About this process we know that it's governed when n goes to infinity by another linear process which is Gaussian. So where eta has normal distribution with parameters 0, 1 half. And also, except this process, we have some fluctuations which are asymptotically Gaussian, which are independent on this linear process, and which are of the size 1 over square root of logarithm of n. So we have such rather strange behavior, and nothing as Brownian motion appears. Now let me explain what is the correlations of the process Ztn. In fact, they are governed by the Gaussian free field, on the plane R2. The Gaussian free field on the plane is a generalized Gaussian process, which is given by the covariance function, I will call it J of Ts equals to minus 1 over 2 pi logarithm of the absolute value of T minus S. Ts are real. It doesn't mean that this covariance equals to just to this covariance function of the Gaussian free field, but it can obtained by some integration of this function, and in the result you have some explicit but long formula. In fact, the appearance of the Gaussian free field in this context is not surprising, because after a series of papers of Borodin, Ferrari, Petrov, and other people, it's rather clear that the covariances of in the systems which are close to random matrix systems often are governed by the Gaussian free field, and we know that the sine process can be obtained as a limit of the Gaussian unitary ensemble. Let me explain this in more. Yes.
So look at this one. So logarithm of n is much larger than t, right? T is between 0 and 1. So in this picture, the fluctuations are very small around the. So you have eta times t, which is order 1, and then the second term is 1 over logarithm of n, or 1 over square root of logarithm of n.
Yes.
So it's tiny.
Yes, that's it.
It's not like the scale you draw it, right?
No, it isn't the scale I draw it. Yes, you're right. Thank you. This is yeah, but it depends on n. Yes. They're very small. But later on, I will explain why is it important to look at this process and why it isn't sufficient to look just after this component. It will be the next part of the talk. But now let me explain about the Gaussian free field. The point is that we can consider the function which I'll call htn, which is called the height function. It's a standard object to study in the random matrix models and in some gross models which are related to the random matrix models. And this is just the number of particles, say, on the interval nt infinity. The problem is that for us this object is not defined, because this number of particles is almost surely infinite. However, if you take the Gaussian unitary ensemble and your process is just the spectrum, the number of eigenvalues is finite, so this object is well defined. And it's expected after this work that I mentioned, it's expected that the behavior of this height function is as follows. At the given moment of time t, it satisfies the central limit theorem, and its variance grows logarithmically, like a constant times logarithm n. But the covariances of this height function taken at different moments of time behaves as a Gaussian free field when n goes to infinity. Despite that the height function in our setting is not defined, we can formally express the number of particles on the interval 0 n through the height function. That will be just the difference of the height functions at the point 0 and the time t. So let me erase. So the number of particles on the interval 0 tn equals to h 0n minus h tn. And then if I formally put this formula to the definition of the process Z, which is expressed through this number of particles, and I compute the variance and I take the limit n to infinity, I will see, using these rules, I will see that this growing term will cancel and only the Gaussian free field will remain, and I will obtain exactly this formula. So despite that the height function is not well defined here, it gives some correct intuition. Now let me also mention something that I forget about the theorem. What is this time tau? Basically, you can put tau to be equal to 1, but if tau is small, you have some nice statistical interpretation. You can think that in order to predict behavior of the process, you need to know it only at arbitrary small time tau, because to determine eta n, you need to know this process only on this interval 0 tau, and this gives you the main order term in the development, and then the rest you can approximate by this limit which you know explicitly. So this is the formulation of the result. If you have any question about the formulation, it's better probably to ask me now, because further on I will explain the motivation, how one can understand that you need to look at the integral and not on the process itself, and how can you see that you need to look at the not only at the main order term but on the error also.
Sorry.
Yes.
Just to be sure, if you fix a t which is not 0, then psi tn
Yes.
tends to a Gaussian and 0, 1 for each t.
Yes. Yes. Exactly.
And the difference psi tn minus psi sn also tends to a Gaussian and 0.
Yes. That's the point, because you do not have.
It's really wide.
Yes. Exactly. That's the point why I need to take basically the integral and why you do not have anything like Brownian motion. So, in fact, it's what I'm going to tell now. Так. Erase this. Motivation. So now let us forget about the theorem. Let us remember that we have this process psi tn, and the only thing which you want to investigate its limiting behavior when n goes to infinity. The first thing that you should do, of course, to study the finite dimensional distributions of this process. And we have the following lemma: fix any times t1, td between 0 and 1, and then let us take the finite dimensional distribution of our process at these moments of time, and we prove that it converges to the distribution of the following vector. We have eta 0 minus eta t1 and so on, eta 0 minus eta td, where eta t have normal distribution with parameters 0, 1/2, and eta t and eta s are independent for any t different from s. This lemma generalizes the Kosten-Lebowitz central limit theorem for many dimensions. So basically you obtain some limiting distribution and you find that it can be represented in such form. And by the way, here you see some trace of this height function, because you can think that eta 0 is a limit of the height function taken at point 0, at time 0, and this is a limit of the height function taken at the point t1. However, I repeat that the height function is not defined itself, but in some limit it is defined. So since we have such a finite dimensional, such behavior of finite dimensional distributions, if the process psi n converges in some sense, then we expect, of course, that it converges to the difference of the processes eta 0, so just constant process, and eta t. But the problem is that the process eta t is not defined in the classical sense because it doesn't live in any separable metric space. It's completely decorrelated in time. And also this difference is not defined in the classical sense. That's why in order to regularize this convergence, instead of studying the process psi t, we study the time integral of our process. And of course we expect that it converges to the right hand side, to the integral of the right hand side. So this is eta 0 times t minus the integral of the process eta s. And here we hope that despite that the process eta s cannot be defined in the classical sense, the integral of it can be defined. Here once more you can draw an analogy with the white noise, which is not defined, but its integral gives the Brownian motion. And trying to realize this strategy, we obtain the following proposition, which actually proves the main order convergence in our theorem. So proposition: for any observable phi, which is L1, the distribution of our process integrated against this observable weakly converges to the distribution of the random variable eta 0 multiplied by the averaging of the function phi over the interval 0, 1. In particular, if we take phi to be equal to the indicator function of the interval 0 t, here we obtain exactly this term, and here we obtain exactly this integral, and the right hand side, this is exactly this term, so we do not observe any influence of this integral. So somehow you can say that this integral vanishes, and the reason in fact is that the process eta s as well as the white noise is completely decorrelated in time. However, for the white noise the correlation is a delta function, but here the variance is delta function. Here the variance is only finite, so it oscillates very fast, and when you integrate it, but with not very large amplitude, when you integrate it, it averages out. So this proposition gives the main order asymptotics in our theorem, because here eta 0 is the same that eta here, and you obtain the convergence of this eta n to this eta. But we lose a lot of information, because at the level of finite dimensional distributions we see this process eta t, and here we lose it completely. So the next thing which we would like to do to recover somehow this process under the limit, and that's why we look at the next order terms, and there in some sense we recover it, obtaining the limit of this process Ztn. I hope that I explained more or less the motivation why the statement of the theorem is that it is. And now let me pass. Yeah.
If you take t not to the 1 but small,
yes,
1 over square root of log n.
Yes.
So that these two terms will be of the same kind of
Yeah, but I mean, you need, then you need to send t to 0.
Maybe you're just considering two crude scale in t, and that if you go on a smaller scale, they will be correlated.
Yes, probably, but then, yeah, then you also should scale t with n.
Interesting, probably, and then you scale it, of course.
Probably it makes sense. Probably it makes sense. Yes, but basically, what I wanted to obtain some just information about the trajectory of the process. That's why I need to look at different scales simultaneously. So now let me pass to the proof of the theorem. As usual, when you want to study behavior of the process, you need to prove two things. The first one is to study the finite dimensional distributions, and the second one is to prove some tightness. Then you will get the convergence of processes. Tightness here is a simple exercise, but what is more interesting is convergence of finite dimensional distributions, about which I will speak now. And to simplify the explanation, I will consider only two-dimensional distributions. That is, now I will prove that the distribution of the random variable eta n joined with the distribution of the process that n taken at some instant of time, say t0, weakly converges to the distribution of eta together with the process zt at the point t0. So that's what I want to prove. To prove this, let me introduce some notion of linear statistics. Namely, let me take a function h, which is measurable bounded function, with compact support. Yeah, and h is a function from R to R. And let me consider the following function shn, which is a function on the space of configurations to R, which is defined in the following way. I take the function on the configuration x is just a sum over all points y from this configuration x of this function taken at the point y. This is just the standard definition of the linear statistics, but now I need, for my purposes, I need to divide here over n, and that's why n appears here. So I take a function, I sum up the values of this function at every point. This sum is finite because the function is compactly supported, and then I stretch this function. For example, if the function h, this is an indicator of the interval 0, 1, then it's one-line computation that the corresponding linear statistics will be exactly the number of particles on the interval 0n. If the number of particles can be expressed through some linear statistics, it's rather clear that the random variable eta as well as the random process dt can be also expressed through some other linear statistics, and this is a simple computation to find the corresponding expressions. Namely, we find that eta n has the form some linear statistics corresponding to the function f. I will write this function later on, minus the expectation over square root of 2 variances of two variances of this linear statistics. Here f, this is just, say, f of y. This is just an integral from tau to the power minus 1, integral from 0 to tau, the indicator function of the set 0s of y integrated over ds. Let me draw it. This is just piecewise linear function. Here it is 0. Then you have linear. Here it is linear, and here it is again 0. So you see, it's very simple function. Then for the random variable eta t0 n, we get a similar representation. This is also a simple computation. It has a form of linear statistics of some function j minus its expectation. And here we do not have any normalization over the variance. Why we do not have any normalization? Because in fact we have the normalization already there in this formula which defines the process ztn. What is the function j? It's also a very simple function. It has, I will not write explicit formula, but it looks like this. Something like this. It's also piecewise linear. So we see that we need to obtain convergence of something which resembles the scaling of the central limit theorem. And in fact, in order to get this convergence, we prove some general central limit theorem for linear statistics. We generalize the result of Kostin and Lebovitz. Now I will formulate it. So theorem, let f and j be real functions, also bounded as usual with compact support, of course measurable. And let us make the following assumption. Let us make the following assumptions. First, we assume that the variance of the linear statistics corresponding to the function f grows to infinity. And the rate of the growth is not important here. As n goes to infinity. Second, let us assume that the function j belongs to the Sobolev space h1/2 of R. So this is the Sobolev space. In particular, this implies that the variance corresponding to the variance of the linear statistics corresponding to the function j is just bounded, but this is slightly stronger. Then we consider the random variables zeta tn, which is just standard random variable for the linear statistics corresponding to the function f, which you look at when you want to prove the central limit theorem. And the random variable zeta fn, zeta jn. This is the same, however, without any normalization. And for the function j. For the function j. Then the result is that their joint distribution converges weakly when n goes to infinity to joint distribution of some random variables zeta f, zeta j, which are first of all independent. So eta zeta f, zeta j are independent. Zeta f has standard normal law, and zeta j has normal law with the parameters 0, and then you have squared h1 half norm of the function j. So let me discuss this theorem first for the marginal convergences. Let us take function f such that its variance of the corresponding linear statistics grows to infinity, and then we have standard central limit theorem. In particular, if you take f to be equal to the indicator function of the interval 0, 1, you will get exactly Kostin and Lebovitz central limit theorem. Here we know that the variance grows logarithmically, and this result generalize the result of Soshnikov, where some closed statement is proven. However, he needs some additional assumptions for the function f. The second convergence is much more delicate, because here you do not have any normalization, but you assume that the function j is sufficiently regular, and then you have central limit theorem without any normalization. And the reason why it holds is the following. So if we take function j at the point y over n, which we are doing when we're computing the linear statistics, it has some very long tails, and because of these tails, you have some very effective cancellations, which allow to have this inequality, that the variance doesn't grow. But if you cut these tails, you obtain something like the indicator function, and the variance will grow. In particular, this regularity is optimal because, for example, the indicator function belongs to the space h1 half minus, and already the variance with such function you cannot prove such theorem because the variance grows here, and we need to normalize over the variance. So this result, in the closed form, is proven by also by Soshnikov. But the main point of our theorem is that we get joint convergence of two different scales: the scale when the variance grows and the scale when the variance is bounded. Let me erase this. The proof of the theorem is based on the analysis of the cumulants. So when you want to prove central limit theorem using cumulants, you need to show that the cumulants starting with the third one, they just go to 0 when n goes to infinity, and the second one converges. In the case when you have growing variance, this is much simpler, because just playing with this variance you can kill the higher order cumulants. But here you do not have such normalization, so it's much more delicate. And in this part you need to use some combinatorial identity, which is due to Soshnikov and which holds only for the sine process. And that's why, in fact, this part holds for general determinantial process with Hermitian kernel, but this part holds only for the sine process. And this is the only place where I use that my process is the sine process. So this is the scheme of the proof. Then you just apply this theorem to these random variables. Of course, the function j satisfies the assumption of regularity, and you get this convergence. So let me finish here. Thank you.
Thank you very much. Are there any questions, comments?
Can you say that when you take integral, you basically study statistics of the sums of eigenvalues rather than number of eigenvalues? Because when you integrate it, you kind of get...
When I study the integral, I study the statistics of the sums of eigenvalues. Let me.
So you basically have delta function for every eigenvalue, and then you integrate it over when it appears.
I don't think so. In fact, I don't think so. I think
it starts to contribute only when you already reach this eigenvalue, right? And then
yes, it starts to contribute when
then you integrate. So
you reach it, but its values it isn't so important.
But integral will be equal to t minus this lambda.
Yeah, so it's somehow lengths between the eigenvalues, but
so
not the precise
you can express it through the sums of eigenvalues. I think that's
somehow yes, somehow probably yes. Yes, I think so.
Okay, other questions, comments?
But for me, it's just the regularization.
Are there any other questions? Okay, if not, thanks the speaker again. And so we have a break until 11:30. So the next speaker this morning is Livio Flaminio, and he will talk about Nil-sequences, multiplicative functions, asymptotic orthogonal powers.
Thank you for the invitation. So, asymptotic orthogonal power AOP for short is a notion that was introduced by Abdawi, Lemanchik, and Delarue in a paper of 2015. And the reason of the motivation for this definition was to give a measure theoretical approach to the Sarnak conjecture on the orthogonality of Möbius functions to zero entropy systems. So before I state it, I will probably need to recall the definition of joinings. So, which is a measure theoretical definition. So if you have two transformation S and T, so S and T to measure preserving transformation, or measure spaces X are mu and Y be nu. So what is adjoining? Adjoining is a measure of S and T is S times T invariant measure on the product spaces. Which has marginals mu n and nu. So we have x cross y, y on this space the transformation S times T acts, preserving the measure adjoining, let's give it a name, rho, and two factors x S mu and y T nu. So it's a way of combining the two measure spaces. It's so, for example, rho mu times nu is adjoining. It's the product joining. If S is equal T, then we also we can put just the measure mu on the diagonal, so you have the diagonal joining. Diagonal joining. Or if S and T are isomorphic, so this is 1, 2. If there is an isomorphism, say phi from X to Y, isomorphism of S and T, then you can put the measure mu on the graph of phi, and that gives you another family, another joining. So GEST will denote the set of ergodic joinings. Of S and T. Now I'm ready to give the definition of Dalauli, Lemanchik and Leroux. So we start with a dynamical system T. And we say that T satisfies our P if whenever F and G are in L2 of X mu with average 0, we have so the lim sup as R and S go to infinity, R and S being primes, of the lim of the sup over all ergodic joinings of the R power of T and the S power of T of the F G tensor G di rho. This is 0. It's more efficient. Okay, the way of thinking of this is that when R and S are large primes, every joining of the power R at T is in fact in a weak neighborhood of the product joining. Because for the product joining, because of this assumption, this integral is 0, so it's saying since the soup is an all ergodic joinings, it's also for any other joining by the Choquet theorem. So all the joinings are actually close for large power R and S of the product joining. So, which explains the term approximate orthogonality. The function f and g are orthogonal essentially. In fact, the motivation and the relation to Sarnak conjecture comes from a dilemma of Bourgain, Sarnak, and Ziegler, which relates, which says the following thing. So suppose I have a sequence of bounded complex numbers. So in the ball of complex ball of radius r, and suppose we know that 1 over n, so the lim sup over r and s going to infinity, r and not s prime, of the approximate L2 product of the sequences R and R and S bar. If this is 0, then this implies that the sequence AN is orthogonal approximately orthogonal to any u multiplicative functions. Bounded by 1. So in particular, the Möbius function is such a function. So, and you can see the similarity from this expression and those one, if for f and g equal, this would be just sampling f along the r power of a sampling of f along the r power of the transformation t, and the other is the sampling along powers of the same transformation, the s power of the same transformations. So essentially this is a sort of, if you think of the ergodic measure which is described by the asymptotic limit of the AN, or that describes the distribution of the coefficients AN, then the analogous property is this. Okay, so, but the advantage of putting this in an ergodic theoretical framework is that this is an ergodic property, so it's invariant isomorphism. Sarnak conjecture instead is a conjecture about continuous topological dynamics. It states something about all continuous functions on a compact metric space for a dynamics of zero entropy. Now, if through the lemma and the AOP property one can prove a similar statement, but now the statement will be valid for any continuous system which is isomorphic to another continuous system which has the same property. Okay, so it's becomes an isomorphism. It's an isomorphism, measurable isomorphism invariant. In particular, for example, we'll see that it holds for rotation, so it holds for any compact metric, for any other topological system which is measurably isomorphic to rotation, such as the Sturmian systems, for example. Okay. So the question is which systems which measurable systems satisfy this property, and already in their papers they El-Abdadawi, Klevancic, and Delarue made the following remark. First of all, is a property AOP is stable under factor. Bernoulli systems do not have AOP. And this implies that AOP implies zero entropy by Sinais-Ornstein's theorem. And finally, another system that does not admit orocycle flows, or orocycle time map. Do not have AOP. But in the same paper that I mentioned before, Bourgain, Sarnak, and Ziegler proved Möbius disjointness for orocycle map. So why is the orocycle flow does not have map? This simply because if you look at HS and HR for R and S some primes, there is always an isomorphism between them, which is the geodesic flow of power log of S over R, I believe, is an isomorphism between these two flows. And if S and R are large prime, but the ratio is small, this becomes, you can put on the graph of this isomorphism a joining which is very close to the diagonal joining. So the theorem I want to talk today is one of the theorem of a joint paper with Franček, Kulaga, Joanna Kulaga e Lemancic. Which says the following thing: every affine unipotent diffeomorphism of a Nil manifold satisfies OP. Well, the Nil manifold for me are always compact, but you cannot compact. So a Nil manifold is just a compact quotient of a nilpotently group. So we start with G. So in fact, in this theorem, the affine unipotent diffeos are become I should say ergodic. Can be considered as a time one map of Nil flows. So the proof for affine nilpotent for affine unipotent map is reduced to one for flows, but like notions of AOP for flows is not well defined. So in fact the proof for affine unipotent is a bit technical, but if instead of affine unipotent we consider the simplest case of translations, I think I can give you today 99% of the proof of this theorem. Okay, so to start with, what is a Nil manifold? So idea of the proof. So G will be connected, simply connected. Nilpotently group. Which means that G, as everybody, is G1 and it contains its commutator subgroup G2, which contain the G k minus 1 derived subgroup Gk, which contains Gk plus 1, which is identity. It's called the central descending series, and nilpotent means exactly that this series terminates. Nilpotents connected simply, they are just isomorphic to Rd and for certain d, and they are, and the exponential map is surjective. Okay, so not all nilpotent groups have a lattice, but if they have a lattice, we have a similar. So if gamma in G is a lattice, G mod gamma is compact. So, but an affine map of a G mod gamma is simply so affine map is simply a map phi associating to phi x u times ax gamma, where A is an automorphism of G satisfying A of gamma is gamma, AU is an element of the group. So when A is the identity, we just have what we call nil translation, nil rotations according to your taste. Okay, so for me today The Nil manifold is G mod gamma. Thank you. By definition, a Nil manifold. I'll give you an example. So example of G can be any closed subgroup of Tn, the set of matrices which have one on the diagonal and anything above. In fact, every nilpotent simply connected nilpotent group has a faithful representation as such a group. So, and in the example of a lattice, you can take Tn, the same matrices, but with coefficient. With coefficient in Z. So, in particular, the Heisenberg group is the group of matrices 1, 1, 1, X, Y, Z, X, Y, Z, R, and a lattice in here is Heisenberg of Z. Okay, for the proof, in fact, we need a bit of structure so on the Nil manifold. So for a Nil manifold, that's always two vibrations which are interesting to us. The first observation is that G quotient by its commutator group is abelian and so isomorphic to some RD1. So we have a map, so the map G to G mod its commutator group is a homomorphism and induces vibrations on a quotient of R. So this is, we said RD1, so this will be a torus of dimension D1. So we have one first picture, we have a torus of dimension T1, and R manifold projects with a fiber which is a Nil manifold, a complicated Nil manifold. This is a functor which is the abelianization functor, okay, that maps to sorry, I forgot gamma. Okay, so this is one vibration, and the other vibration comes from looking at another projection. So we look at G divided by G K. Okay, or rather, let's look at the actions. GK is a subgroup of G mod gamma. So it acts on the left on G mod gamma, and it acts, but the stabilizer will be acts on G mod gamma with stabilizers GK quotient GK intersect gamma. And since GK is also abelian isomorphic to certain RDK, the fibers are tori of dimension dk. So we have the other pictures, which is G mod gamma, fibers with fiber some tori of dimension dk over the compact manifold G divided by GK gamma, which is if you divided your group, well, we don't have it. If you divided G by the last derived subgroup, you have just a nilpotent subgroup, which is one of degree of nilpotency, is one less. So we have two fibrations, one with a complicated fiber and an easy base, and another with a fiber which is a nil manifold of lower degree, but with a very nice fiber. Okay. And so one case in which all this can be seen at once. So for G is the Heisenberg. Then the two cases coincide, and so I don't think I have Heisenberg. Oh yes, it's here. So here GK is simply the center, which is this coordinate there. So quotienting by there means looking just at the coordinate x and y. And when we multiply matrices, we add x and y's. So we have a torus. And so the two vibrations actually coincide. We have a torus spanned by x and y. And you have a fiber, which is the orbit of the subgroup Z. Okay. All right. So back to the. So this is the structure of the every Nil manifold. Well, let's go. So we have now a G mod gamma Nil manifold, and we have an ergodic translation. Well, there is a very nice theorem of Auslander-Green and that tells us when such translation is ergodic. So LU is ergodic and minimal if its projection on the torus on G2 gamma is an ergodic translation. And we know what that means. Means that the projection on LU bar means just U bar is irrational with respect to the lattice defined by the torus. So now we want to understand, in order to go back to the theorem, we want to understand joinings of Lu power r and Lu power s, and for this it will not be important that r and u are prime, it will be just sufficient that r and s are relatively prime. So what are joining of Ru and Rs? Well, the projection on the torus, well, before we go actually through the joinings, let me observe that the other thing that we need, I can write it here, L2 of G mod gamma is in fact now through the second of the fibrations we can write it in a very simple way as a direct sum of orthogonal L2 subspaces, where this is the space of function in L2, which have the property that when I multiply them by an element in the Z in G2 in GK become multiplied by a character. So the sum is of all characters in the torus decay of the last vibration. So these subspaces are mutually orthogonal, and because they are orthogonal in the fiber of this vibration, and so we can simply pick up functions from these subspaces. And one remark is that here you have in particular the trivial character. Trivial character corresponds to functions that are invariant over the fiber. So in fact functions that are defined on a Nil manifold of 1 degree less of nilpotency. So we work on inductions on the degree of nilpotency of the Nil manifold. Okay? So, like in every induction, proofs usually starts with n equal 1, right? So the first case I consider is the torus. Okay. So now let's suppose that G is Rn, Rd1, and so we have a torus, and the joinings are just the joinings of two of an irrational rotation of this torus. So here is my torus Td1, and here is another copy of the torus. On this torus I operate by the translation Lu to the R, and on this torus I operate by the translation Lu to the S. Oh, but let me write bar to be because this picture will be used again. Okay, so this translation is the same thing as the translation by R U bar, and this is the translation by S U bar. Okay, so what are the ergodic joinings? Ergodic joinings are just joinings of the subgroup of slope R over S, right? Every ergodic joining is supported on one. Why it's a full subgroup? Because ergodicity implies that the projection on each coordinate is the full torus. Okay, so actually here I've designed a torus of the same dimension as the basis. right? And now, suppose I take a character, two characters, key L, key M, and I integrate it with respect to an ergodic joinings on this product of tori. Well, this is the same thing as the integral on this coset of this subgroup. And you see that now this is 0 unless a miracle occurs, because the characters are just e to the I, L, oh, let me write it like U, like Jensen, this is just L, A, Y, Y plus L, M, M, Y, d rho, which I integrate on a subgroup which has a slope. So I can replace for y, essentially, there are two coordinates in y, so there is y1, y2, there is, ly1 plus my2, d rho y1, y2 on the product. But y1 and y2 are proportionals, right? Up to unaffine translations. Okay, so this is 0 unless R and S unless this exponent is 0, which can only occur for infinitely many R and S. R and S are going to infinity in our game, right? While the character Lm is fixed, right? So as R and S go to infinity, in fact, right away this becomes 0. Okay, so that means that eventually all the characters are killed by R and S, and by density of the characters in R2, we're done. Okay, so the step 0 works. Step 1. And almost done. Because the general proof for translations is just the same argument, but this time we apply it to the fiber. So now let's assume that key 1, suppose that F belongs to, I didn't give a name to this space, it would be probably a good idea to call this subspace H key. So suppose that F belongs to H chi and G belongs to H theta. And we are now in a general situation, and we have rho adjoining, an ergodic joining of a translation of any manifold to the power R, and this is joining to the power, same translation to the power S. Okay, so we said we had the two pictures to consider. So on one side we have G mod gamma times G mod gamma, on which Lu to the R times Lu to the S acts, and this projects on one side on G mod gamma L R U, and on the other side L G mod gamma L S U. But these guys project on a tori with a with a ergodic rotation to the power L. And same for this. So we have a diagram, and we can put, if we want, here the product of these tori, right? So all right, so what do we know? We know already that if we since this is ergodic up here, it's ergodic in each component, and it's ergodic on the product. Okay, so and on the other hand, we know that so it has to project on some irrational rotation on the side that go with speed which are relatively speed which are r and s. On the other hand, we have the other picture of the vibrations in which in the same picture, if you want, in this upstairs here product, we can write this as a circle bundle over some Nil manifold, right? So what do we know? So there will be also a product like this. So what do we know? We know that the joining up here is an joining of a translation of an nilpotent group. So it's orbit closure. I mean, these joinings are classified by Ratner, if you like, but it's just a translation of nilpotent is just an orbit closure of some group. So we know that whatever this joining is, it lives on the orbit of a subgroup. What do we know of this subgroup? We know of the subgroup that it projects here and here to the full algebra, right? So there are some elements in this subgroup, whatever it is, that projects exactly to S times the generator on one side, and R times the generator on one side, and S times the generator on the other side, right? So there are elements in the base that are image or projection of generators of this subgroup. When we take k commutators, k-fold commutators of this element, we end up now in the subgroup of the upper level, g to the k. Right? And each time we take a commutator of two elements that have been multiplied by s, the commutator is multiplied by s squared. Right? So in the end, whatever this group is, it will contain in this fiber subgroup, the fiber now in the product is the product of two fibers. Right? So the fiber will be a product of two tori, and on this side it will have a slope s to the k, on the other side we'll have a slope r to the k. Right? So the same argument that we said before will say that two elements which in the fiber behaves as characters will be killed once s, r, and s will be sufficiently large. Okay. Okay. Where should I go back to? Okay. So, okay, I start from here. There is a group that supports the orbit of this measure. Okay, this group has generators that projects onto the factors on each side. Okay, the generators on this side, I can take generators and consider brackets of these generators. The bracket of two generators, so if they are both multiplied by s, the bracket gets multiplied by s squared, right? And lives in G2, right? If they started in G. Bracket of a bracket live in G3. Bracket of a bracket k-fold live in GK, right? So in the end, I will have elements, my group will have elements in the fiber, which are the product of the two fibers of the Nil manifold, right? So the product of two tori of the dimension decay. In the fiber, we'll have generators that have slope s to the k on one side and r to the k to the other side. And r and s, so as r and s go to infinity, any function which behaves as a character in each fiber of these tors, fixed characters, will be killed. Right? And so exactly the same argument as before. Okay? So that shows that as R and S go to infinity, any f and g down these spaces will have eventually average 0. Okay? It finishes the proof. Okay, thank you.
Any questions, comments? Yeah.
This was just for translations. The theorem is more general. This was just for translation. Can you talk a little bit about the general case?
For affine map, if you take an affine map, so you have an automorphism, right? So phi of x gamma is u of x gamma. So you can now make a you can do the suspension of this map. The suspension of this map is another Nil manifold. Okay, of one dimension larger. So now you have the situation as a G mod gamma is a cross section of some flow. All right. Then you have to relate the joinings of the bases to joining of the flow. Every joining of the base can be pushed to a joining of the flow, right? And then you have to argue on a similar way, but now the structure, the fact that you have added a new element to the Lie group changes completely the bracket structure and the degree of nipotency of the manifold, right? So you will have to argue in a different, somewhat in the similar way, but on the new Nil manifold and show again that this group. You argue for the flow and you say what are the groups, the joinings of this group. Again, this is some Lie group, and you go for the generators of this group and work in the same way. But it's much longer to explain.
Questions, comments?
The most difficult case actually is the case where you consider disconnected nilpotent groups. And there you will need a theorem of tau Radziwiłł because it doesn't work for a rotation for a finite rotation, right? For a finite rotation it's Davenport if you like, but you need another argument for AOP that doesn't work for rotations. Okay. So that's the most difficult case, considering not disconnected groups.
Okay. If no other questions, let's thank the speaker again. So understand this is the end of the day. Are there any announcements or? Okay.
See you tomorrow.